degree 2t polynomial P that approximates the function f. So this means that it is a distance at most 1/3 on all inputs in the domain, and it's bounded between 0 and 1 for all inputs, for all possible inputs. So it's quite an important condition here. So it's actually, it says that if you run your algorithm on an input outside of your domain, you have no guarantees, but it's still an acceptance probability should be a real number between 0 and 1. Okay, so these are two conditions. Okay, and so if you can prove that there is no such polynomial, then you immediately get that there is no t-query quantum algorithm that evaluates the function f. Okay, and this condition here can be expressed as a dual polynomial using standard linear programming duality. So I will come back to dual polynomials shortly. Okay, and the second method, it's the adversary method, and so this is a version, it's a general adversary method, so-called is version due to Hsieh and Spalek. Okay, and in this case, I assume that there is an x times y matrices. So remember, x and y were positive and negative inputs, respectively. Okay, so there is an adversary matrix gamma, like with rows labeled by x and columns labeled by y, and which I called derived matrices gamma j for each j in n, where n is the number of input variables. Okay, and so this matrices satisfy two conditions. So the second condition is easier. So the spectral norm of each gamma j is bounded by 1. So it's kind of a normalization condition. And this first condition is more tricky. So it says that gamma j agrees to gamma on all pairs xy, whenever xy is not equal, xj is not equal to yj. So this means that you can get gamma j from gamma just by changing, only by changing entries with coordinates x and y, where x and y agree on the j's input variable. So kind of this means that you can change the variables which are not seen by the query, because the query, the j's variable, you'll get equal results in x and j. So that's the x and y. So that's the like the intuition why it works. Okay, then you can prove that any quantum algorithm distinguishing x and y with bounded error makes omega spectral norm of gamma queries to the input string x or y. Okay, and so let me compare the two methods. So they're somewhat complementary. So there are problems with easy lower bounds by the polynomial method. So examples could be collision. So it's was proven by Aronson and Hsieh. And also k-distinctness. So k-distinctness is a kind of interesting, more recent developments where there were like improvements, like using especially the dual polynomial method. And it's still not tight, a lower bound, but it's very close to being tight. Okay, and vice versa, where problems were much easier, where adversary method is much easier than the polynomial method. That's, for instance, the not end tree, which was proven by Ambrinis, like by a very simple adversary argument. It took like 10 years to develop polynomial lower bounds. And for, say, for the k-sum problem and for left triangle problem, the polynomial lower bounds are not known as far as I know. Okay, and another important condition that observation is that the adversary method is tight for bounded error. So this means that in principle, you can, for any function, you can find tight adversary lower bound that gives the precise lower bound, while the polynomial method is probably not. Okay, and so let me state the result. So in theory, since the adversary method is tight, there ought to exist an equally strong adversary lower bound for each polynomial lower bound, just by like utilizing this theorem. But there was not known like direct connection, like direct construction of how we obtain this adversary lower bound. Okay, in this talk, I will explain a very simple, direct mechanical way of transforming a dual polynomial into an adversary lower bound. And so if you take a dual polynomial, you can actually see say that, okay, you can prove that, consider it as a polynomial lower bound, but now you can also consider it as an adversary lower bound of a very specific form that I will explain shortly. Okay, and so the motivation for this is that this should allow a possible combination of the two methods and gives a better understanding of both adversary method and the polynomial method. Okay, so let me go shortly through the proof. So first, I will return to dual polynomials. So I will not define them in formula, I will just explain them. Okay, so remember we had this task of distinguishing two sets of inputs, capital X and capital Y. Okay, and so this degree T, that was a lower bound that the dual polynomial gave. So it can be, this linear optimization problem can be expressed in the following way. There exist two probability distributions, mu and nu, with the joint supports tilde X and tilde Y, with the following two properties. First, they are well correlated with X and Y respectively. Okay, so I will not define what well correlated means, but okay, it's easy to define. Okay, and the second condition is much more interesting. So this it says that these two probability distributions are perfectly indistinguishable by assignments of size not exceeding t. Okay, so this means that if you take an assignment alpha of size t, this means that you fix the values of t of your input variables. So if someone gives you any t elements from a string, sampled from mu or sampled from nu, they have exactly the same probability in both distributions. So this means that given the value of these t elements, gives you absolutely no information whether your input is sampled from nu or your input is sampled from mu. And so let me note also that this condition of having like indistinguishability by assignments is also used in classical lower bounds quite extensively, but there is no condition of being perfectly indistinguishable. Like somewhat indistinguishable distributions are still going to give lower bound. But in the quantum case, as this is demonstrated by this dual polynomial, we really need this perfect indistinguishability. Okay, so and we will see how this is used in the adversary lower bound. Okay, so the consequence of what is written here is that it suffices to find a matrix gamma prime for distinguishing these new sets tilde gamma for distinguishing tilde X and tilde Y. And then we can get the matrix gamma for distinguishing X and Y just by restricting this gamma tilde to the inputs that are allowed. Okay, and you can, it's not too hard to prove that this still gives a good lower bound. Because, for instance, derived matrices will have norm less than 1 because this is a submatrix. And you can also prove using correlation that this new matrix still has a good lower bound, like a large spectral norm. Okay, and so I can restate the problem. And so I'm now going to talk about the following problem. So we have two probability distributions, mu and nu. And now I removed tildes because okay, I just have X and Y. So two disjoint subsets. And that the same conditions, they're perfectly indistinguishable, okay, by assignments of size at most 2t. Then there exists an adversary matrix gamma for distinguishing X and Y with the norm equal to t plus 1. So now I will explain how I get this matrix gamma. That was gamma tilde on the previous slide. I just stripped gamma, all tildes because I won't need them anymore. Okay, so this is the technical part of the argument. Okay, this slide exactly. So so I take an assignment alpha of size that doesn't exceed t. So this means I fix at most t input variables, and I define two vectors, like in the set with input bases given by the with bases given by the inputs. Okay, so the first one, okay, I'm sampling from mu, like all the elements which agree with the assignment alpha. Okay, and I'm putting a square root as usual. Like mu is the probability to get an amplitude, taking a square root of the probability. And v gamma is the same thing. I'm taking mu, which is supported on gamma. Okay, such two vectors. Okay, and so the main idea of the argument is this equality here. Okay, so what is said here? So here is the inner product between these types of vectors. So you think about this. Well, this means that this can be written as probability as x sampled from mu. The input agrees both to alpha and assignment alpha and assignment beta. Okay, because these are the only. So this condition means that they are non-zero here. Okay, and if they are both non-zero, then they both have square root of mu x. They are multiplied, okay, and you get m of x. So it's the sum of m of x becomes. Okay, and by perfect indistinguishability, okay, you can take a look what this means. So this means here that either that x alpha and beta are either contradictory, in which case the probability is 0. If they are not contradictory, they give an assignment of size at most 2t. By perfect indistinguishability, we have the same probability for nu. Okay, and by the same argument, this is the inner product between v y's. Okay, and so we have inner product equal to inner product. Hence, for each k which is less than t, for each integer k that is less than our bound t, there exists an isometry w at most k that maps all v alpha x into v alpha y for all alpha of size at most k. So it's a well-known result. So inner products agrees, there exists an isometry. Okay, and also assuming that 0 on the orthogonal complements of the span of these vectors here. Okay, so this actually is the main result why we need perfect indistinguishability to obtain this isometry here. Okay, and so the adversary matrix is just the sum of these isometries. Well, as easy as that. Okay, and let me sketch why this works. So, so by definition, isometry w at most k maps v alpha x into v alpha y. Okay, and if I'm allowing assignments of larger and larger size, I get more and more vectors in my span. Okay, so I have this inclusion here, this chain of inclusions, where what I mean here, that there are isometries, and the domain of this isometry is contained in the domain of this isometry, and they agree on their common domain. Okay, so I can say this is an inclusion if I consider them as pairs of mappings. And from this, I get this matrix gamma, which is the same matrix as on the previous slide, has norm t+1, which is attained on w at most 0. This thing because it's contained in all these subsets, on all these mappings. So it's counted t+1 times in this sum. Okay, I can even see what is the spectrum of this matrix gamma. So the spectrum has like all integers from 0 to t+1. Okay, and the second condition, I have to show that the derived matrix gamma j has norm at most 1. So here is the idea that I define a slightly different isometry w prime, which is at most k. Okay, and so this is the same definition. So it maps v alpha x into v alpha y. But for all assignments of size at most k, that fix the value of j. So I'm only considering assignments where the value of the variable j is fixed. So I know that this value, the value of this variable is given to me, this assignment. Okay, and as before, it's 0 on the orthogonal complement of these vectors. Okay, and so the first claim is that it satisfies this condition. So this is a direct sum or block diagonal matrix. So it's 0. The interest is 0 whenever xj is not equal to yj. Why? Because alpha fixes j, and so if I have a fixed value of j here, it maps to the same fixed value of j here, so it doesn't go outside of this subspace. So for j equals, all the vectors with j equal to 7 are mapped to the vectors with j equal to 7, so they're living in that block. So it's the sum of isometries becomes along the diagonal, so it's a block diagonal matrix. Okay, and the second claim that this primed isometries intertwines in this chain which I had previously. Okay, so this inclusion is easy to see because I'm having the same size, but I have additional restriction on the assignments which I take. So this means that this isometry is smaller than this isometry. But on the other hand, you can also prove this inclusion because you can write every isometry of size, say 1, as a sum, which doesn't fix j, as a sum of assignments where you fix j just by taking the sum over all possibilities of j. So assignment where you don't fix j, you can write as a sum of this where alpha x, where alpha fixes j, but just going through the sum for possible values what xj can take. Okay, so that's the idea. Okay, and therefore, the derived, I can define the derived matrix like this. Okay, so this is original gamma. Okay, I'm subtracting this primed thing. Because of this condition here, it's a valid adversary matrix. So I'm only changing the entries where xj is equal to yj. Okay, and so this is written here. Okay, and on the other hand, the norm of this matrix is 1 because it's isometry from perpendicular subspaces. So, okay, so this is say W0, or should be at most 0, sorry, is here. And for instance, this thing, so it's say less equal to 1 and primed less equal to 1. So this is a difference. So this means it lives in the orthogonal complement of this of the domain here. So it's orthogonal to W0. So the domain of this isometry is orthogonal to this thing. Okay, so so they have orthogonal domains. So and they are all isometries. So their norms are 1. Okay, so that's the whole proof. Okay, and so to summarize, so we have shown that the dual polynomial is an adversary bound of a very specific form, and this specific form is really based on having this perfect indistinguishability, because as soon as we don't have this perfect indistinguishability, so it becomes much more harder to show that the norm is behaves as it should behave. Okay, and so this is also like one observation that raises a lot of questions which are open and can be discussed. Okay, so can this form be generalized to obtain a more convenient version of lower bound based on dual polynomials? So this means, can we somehow generalize? So we know that dual polynomial is a adversary bound of a very specific form. Can we somehow relax this form and get something more a stronger lower bound technique? Okay, can we explain when and why polynomial method becomes non-tight? So we know the adversary method is tight, so this means that maybe we can see that why lower bounds of this specific form fail. Okay, maybe you can give reverse directions from a polynomial method to adversary method for some specific cases. Okay, when we can show that we can assume without loss of generality that this specific form works. For instance, we know that there is a collision problem, and we suspect that k-distinctness are in this class. Okay, so we crucially use this perfect indistinguishability, as I said. So can non-perfect distinguishability can be used of any help? So it's a very interesting problem, I think, and I don't really have a way to address this. Could be very interesting to solve this. And finally, can this be generalized to completely bounded forms? So which is a generation of a polynomial lower bound. Okay, so that's it. Thank you.
Any question? Yes, thanks for the nice talk. So I have a question about the part of completely bounded forms. So
Yes.
in that case, it would be in principle possible to also go the other way around, right? From adversary matrix to a completely bounded form.
Yes, but completely bounded forms are known to be tight, so there should be conversions in both directions. Right. Yes, you're right.
Is there any hope that you can find a construction that maps an adversary matrix to a completely bounded form?
I think it's possible. Yes, I don't know. I haven't worked on that too much.
Any other question?
Thank you. I was wondering, you mentioned that some problems are easier to lower bound with the polynomial method versus the adversary bound. I was wondering if you think that this mapping might inform us on how to construct adversary matrices that are, I don't know, nicer or easier to analyze for problems that have been historically difficult, like element distinctness with small alphabet size, or if just there are new ways of thinking about constructing bounds, like starting in the adversary method.
I think yes, that what I said on my last slide, that both of these things are valid. So this could give, like, you can take a look at the adversary bounds that you get from this dual polynomial, and maybe you can see how you can do something with this. Maybe you can combine them in various ways so that it's not from a dual polynomial, but it behaves similarly in a way. So, but even if you take lower bounds for K-sum and left triangle, so they use a similar ideas of indistinguishability and extension, but the difference is that they also have like a more structure to them. So it's quite possible that you can take these ideas of having structure and add these powerful techniques of dual polynomials to get something interesting.
Thank you.
Any more questions?
Can you hear me? Yes. I was wondering if the polynomial method can be used in principle to general state conversion problems, and where this work would fit in this direction.
Yes, you can certainly use polynomial method for general state conversion. For instance, there are results that are very easy to prove. For instance, that you can, it's hard to generate a state of the firm like which is 99% 0 and 1% parity. So you can easily prove that you have to use a linear number of queries to generate the state. It just follows from polynomial method just almost instantly. But for the additive adversary, you can prove that you cannot prove this for amount. Yeah, so yeah, you can use it, but I'm not aware like of a general formulation of this technique that would be similar like for state conversion for the adversary method.
Thank you.
Okay, so let's thank speaker again.
Yeah, I think it changed the font.
So this is also
Yeah, the actual.
yes. So this is what
This one.
here. Yes.
Okay, so let's have a second talk. Second talk is by Jordi. It's about quantum PCP.
Yes, thank you for the introduction. This is based on joint work together with Harry Buhrman, now at Continuum, and Jonas Helsen at CWI. And it will be useful first to set the stage a bit to recapture the definitions of QMA and the local Hamiltonian problem, even though you might have heard them 1,000 times. So QMA can be viewed as a proof system between an all-powerful prover, Merlin, that sends a polynomial-sized quantum proof to Arthur, which is a polynomial-time quantum verifier. And then basically, for any problem, a promise problem A is contained in this class QMA if there exists a polynomial-time verification circuit which uniformly generated V, such that if it's a yes instance, then you will accept the input X and the proof with high probability. And if it's a no instance, you will reject with high probability or accept with small probability. And it is known that you can capture the full power of QMA, similar to how KZ captures the full power of the class MP, by considering a generalization of KZ, namely the K-local Hamiltonian problem. And in this problem, you're given a description of Hermitian operators Hi, each of which acts non-trivially only on a subset K out of n qubits. And you're also given some parameters A and B, which are lower bounded by some delta, which we call the promise gap. And then your task is to decide whether the ground state energy, denoted here for the ground state by psi 0 is either small, so smaller than A, or greater or equal than B. And they are actually inverse polynomially separated. If that's the case, then it can be QMA hard, or capture the full power of QMA. So it's known that reductions exist, of course, in both directions. So I've made the arrows here black to indicate that you're just Karp reductions, so normal classical polynomial time reductions, and they go in both directions. So if you consider, instead of QMA, the trivial circuit verification problem, which is basically the definition of QMA as a problem, that you can do reductions between both of them. Oh, so then onto the quantum PCP conjecture. It can be formulated in a similar way. So for defining it as a proof system, we again consider this all-powerful prover Merlin that sends a polynomially sized quantum proof to this polynomial-time quantum verifier Arthur. And now we're going to consider a more restricted version of what Arthur can do. Namely, he's only going to act or going to access a small part of this quantum proof. And then if you write the definition in full, I've taken here the definition from the work by Hardenhoff and others, which to my knowledge first defines the class QPCP. And we'll come back to actually this definition, or like how to define it later. It's actually the promise problem is in this class if you can actually just take some distribution and you pick some of the qubits out of this larger proof, but only Q of them. Then in the yes case, if high probability, there's a proof that makes you accept. In the no case, then for all proofs, it makes you accept or also reject the high probability. This is then called the proof checking formulation of the quantum PCP conjecture. And it postulates actually that there exists a constant Q such that you can capture the full power of QMA by a protocol that works like this. So then again, we can define it also in terms of a local Hamiltonian problem. Again, local terms acting on the quantum state, same definition as before, but now there's a crucial difference. So note that actually because all the local terms are actually normal, so they've operator norm is bounded. So 1 over m ensures actually that the total operator norm of Hamiltonian is bounded. So actually this delta being constant means that it's constant relative to the operator norm. So the gap's actually much bigger now than what we had before. And then the local Hamiltonian formulation actually states that this problem is also QMA hard. But now onto the reductions. So again, from the local Hamiltonian problem to the class QPCP, there's a normal classical polynomial time reduction. But in the other direction, I've made a golden arrow because we only know so far that this can be done through a quantum reduction. So you need to run some kind of quantum algorithm to transform the trivial QPCP complete problem and with the surface verification to a local Hamiltonian problem. And the fact that it has to be a quantum reduction, or how you should do it, was I think first actually pointed out maybe in original work, but definitely in this review, but never really formally proven this way, but a sketch here how you should do it. And there were some works later that actually, in some restricted settings, did this reduction. And this whole work actually started basically as an exercise to basically perform this reduction and just see what would happen. And didn't expect it to turn out to be the case, what we had so far. Because actually it was already raised in this first work to define the class, one has a lot of freedom in defining the class QPCP, similar to how one also has some freedom in defining the class QMA. For example, recall this recent very nice review paper about the 7 phases of quantum MP or QMA. So the question was already raised like a long time ago. How robust is actually this definition that I listed to you of QPCP? Or is it how robust is it to making changes to this definition? For example, adaptive versus non-adaptive queries, does it make a difference? Do we have to allow for quantum preprocessing based on the input? Does it change the class? For non-adaptive version of the class, can we even consider just uniform distributions? Similar to how you can ask the questions for QMA, what about if you consider multiple unentangled provers? So you go to like a QMA-K kind of question, or consider classical proofs. What will change then? And on Thursday, I will also give a talk that talks a bit more about this classical proof part. And so the main results of this work are that the non-adaptiveness is actually not restrictive for quantum PCPs when the number of proof queries is constant. And you can even pick the proof indices just uniformly at random, but only from a subset of all the possible index combinations. So it makes this class actually very robust, which is a good thing. We also showed that if the Q local Hamiltonian problem is contained in QCMA, then actually this class is contained in QCMA. So this links actually the local Hamiltonian problem, a negative result on that to a negative result being implied for the actual class of proof checking. And we also showed that if QMA-K has a constant query quantum PCP for any K larger than 2, or equal to 2, but up to some polynomial in N, then QMA is equal to QMA2. So actually this connects two of the biggest open problems in the quantum complexity theory. And we also give in the main work, which is an archive, also some oracles relative to which the quantum PCP conjecture is false, which you would also expect. Also in the classical case, are oracles to disprove the classical PCP theorem. So this is more as an exercise that we show actually you need non-relativizing techniques just as you need classically if one wants to prove the quantum PCP conjecture. But this will not be talked about during this for this talk. So it turns out that this quantum reduction that I mentioned turns out to be the key in getting all these results. I played around a long time by trying to adopt classical techniques in getting like, these adaptiveness results, but I couldn't get anywhere. And then it turned out that this reduction was like actually the whole key to get all these results. And it turns out to be not as straightforward as was sketched in this review paper, but it comes at the reward of being a very powerful tool in getting many of these results and showing properties about quantum PCPs. So the first difficulty that actually arises, what I mentioned before, is how should one define a quantum PCP? So we want to give a definition that is still general enough to capture a lot, but we also want it to be specific enough to be able to do these kinds of reductions. So we define it actually in the following way. So first of all, consider the possibility of multiple unentangled quantum proofs to capture this power of multiple unentangled provers, similar for QMA-K. And then we consider an adaptive version. So what actually happens, you start with the input and some ancillas and 0. You apply a first circuit, and then you're going to perform some measurement on a very small subset of the qubits to determine which kind of qubits you're going to be queried. And queried here basically means if a proof hanging in the sky, you take out one qubit or maybe a couple of qubits out of it, then you're going to activate the next circuit on this qubit as well as the remaining state that you have after applying the first circuit. You're going to repeat this for, did some symbols disappear? Anyway, hopefully it is clear from what I'm saying. So then you're going to repeat this process for a couple of times, namely Q times for the number of queries. Then you make one final measurement of a single designated output qubit to determine whether to accept or to reject. And this is then, at least how we view it, it's very specified, but still general enough to capture what the quantum PCP should be able to do, because it also captures, of course, non-adaptiveness and preprocessing by a quantum circuit. And then what we show actually, so you give a lemma that if you consider Vx to be the circuit that has this input x hard-coded into it, then this basically induces a Q local Hamiltonian. And so that actually the probability that a circuit accepts a certain proof is equal to 1 minus the energy of the same proof or the state with respect to the Hamiltonian Hx. And then the whole idea is, of course, that you need to design some quantum algorithm that actually quantumly learns this Hamiltonian up to epsilon precision, and we show this can be done to epsilon error in operator norm in time as a polynomial in the input size n and 1 over epsilon with high probability when q is a constant, so for a constant number of queries. So the spectrum of this Hamiltonian H then directly encodes the acceptance probabilities of this verifier. So this means if this verifier, this QPCP verifier, originally had a constant relative promise gap, so completeness and soundness parameters gap, then it will preserve this constant relative promise gap, which is exactly what we want for a Hamiltonian in the quantum PCP setting. However, there might be a potential problem now. So the Hamiltonian we get out of this reduction is actually of the following form, which we call the A form. It's a sum of local terms Hi, but we only have a promise on the total spectrum that like all its eigenvalues are between 0 and 1, so it's PSD. And of course, this implies that also the local terms have their operator norm, or like their is bounded. But we'll see why this is a problem later, because the useful QPCP formulation, actually this is 1 over m there. So you have 1 over m sum over these local terms, then a promise on the operator norms of all these local terms, or actually the spectrum of all these local terms. And of course, both have still this constant relative promise gap, and they are used interchangeably in the literature. But why is this a problem? So how would you then usually put the local Hamiltonian quantum promise gap back into QPCP as a class? You would usually consider Kitai's energy estimation protocol, first used to actually show that QMA contains local Hamiltonian problem, even with smaller promise gap. And this is actually a non-adaptive QPCP protocol for Q local Hamiltonians. So what you do, you consider a Hamiltonian of this B form with all these local terms Hi, and you consider the spectral decomposition of each of these terms, which is given here. And then you define this WI operator, which basically acts on now Q qubits from the proof plus an extra register containing only a single qubit, and it applies some kind of rotation which depends on the energy that you get from measuring this local term. Then the protocol is actually very simple. So what you do, pick an I uniformly at random, apply WI to this k qubits that correspond to this WI, and also the extra register A, measure the register A, and then you have to see if you measure 1. And you can very easily show that the probability that you measure 1 is actually equal to 1 minus the energy of this Hamiltonian. And it's worse because it's 1 over m is actually there. So it will only work for form B. Because for the problem with form A is you don't really know a priori where the energy is going to be. So you don't know what distribution you have to pick. And to work around this, we use the following trick, which we call local norm smoothing. I'm sure this must have been known in the literature before, but we couldn't find it anywhere. And the idea is actually that you take this Hamiltonian in this A form, and you make some transformation to bring it to the B form. So you have an n-qubit Q local Hamiltonian, consisting of these local terms Hi, and they're all PSD, all local terms. Then you consider them having a promise gap of gamma, then you can transform it to a 2Q local Hamiltonian Q, which is of the B form, and the promise gap is now some constant times this gamma divided by 2 over Q. So note that if, of course, Q is constant and gamma is constant, this will remain constant, which is good, which is what you want for the QPCP. And the idea on how to prove is actually it's pretty simple. You have to exploit the PSD-ness of H to bound the total operator norm. And then you greedily combine terms together to actually to spread out the operator norm over different terms. So you combine at most two terms together during the whole procedure, so the locality grows at most by a factor of 2. So now basically all the results we get are based on the following general strategy, which utilizes this reduction. So the idea is that any class C, which contains BQP, can actually perform this quantum reduction. So it can actually learn this Hamiltonian. It's induced by such a QPCP verifier. And then actually, we don't really need to do this, but it is easy to do it in the proofs. You can actually round the reduction in such a way that conditioned on the reduction succeeding, you will always produce the same Hamiltonian. So the prover exactly knows which Hamiltonian you're gonna get out of the reduction if you succeed. Then any local Hamiltonian through local norm smoothing can be brought into the standard B form using the lemma I just showed you before. And then one can use the standard tools or generalizations of standard tools from Hamiltonian complexity theory to solve the corresponding local Hamiltonian problem or manipulate H before you can actually solve it. So let me give two examples of why this is actually useful here. So going back to this question of adaptiveness versus non-adaptiveness, I told you that actually this adaptiveness does not increase the power of the class, the number of queries is constant. So the sketch of the proof goes as follows. So K here is 1. So if I don't mention K, remember there are not multiple provers. The QPCP Q verifier induces a Q local Hamiltonian, which can be quantumly learned up to high precision with high probability in polynomial time using a quantum circuit. Then H can be brought into the standard form using this local norm smoothing. And then we can estimate the energy of Q using Kitai's energy estimation protocol, which is in fact a non-adaptive QPCP. And then using standard weak error reduction, we can boost the promise gap back to a half or any constant we want by maintaining a constant number of proof queries, albeit a larger constant. So then for this multiple prover QPCP, so I told you that if this class QMAK has a constant query quantum PCP for any k from 2 up to poly n, then QMA is equal to QMA2. Again, we have to learn this Hamiltonian up to epsilon precision using the lemma I gave you before. And then this Hamiltonian actually now induces not a normal local Hamiltonian problem, but a k-separable Q-local Hamiltonian problem, which can be shown to be in QMA by a slight simple generalization of the protocol by Joao and Santha. This is over 10 years ago. And then we know, of course, that QMA is contained in QMA k for any k larger than 1. Now, by assumption, this is contained in this class QPCP k, q for some k and q, which is then in QMA, and this actually then proves the theorem. We also have some open problems that are still left. So locality reduction. So a lot of works regarding QPCPs, for example, the one by Nijssen with our Harrow from over 10 years ago, and also the review paper, they actually they point to a result by Bravi and others that actually shows that, or they look about to Hamiltonian Getches reductions, Getches to reduce the locality. And actually, so the question is whether is the two local Hamiltonian problem already complete for a class QPCP, even the number of queries is larger than 2. And we think this might actually not be the case, contrary to what is claimed in the literature, because this Getches construction, it only works, so it only preserves a constant relative promise gap when each qubit participates in only a constant number of terms. And actually, based on an argument by Nierke and Min-Hsiu, where they give some evidence on why Bernau-Harrow might not work for 4 local Hamiltonians, we can give a similar argument that we give in the main paper, that if such a reduction would exist, that would map, would reduce locality of Hamiltonians, was also preserving the constant relative promise gap, even when the degree is somewhat larger, then maybe you already have a direct way to disprove the quantum PCP conjecture. So there's still an open question, like, to look into this. Also, our techniques, because we use this quantum reduction, we can only learn Hamiltonian up to some precision. So we're never able to preserve perfect completeness. So it's still an open question whether quantum PCP of perfect completeness, whether similar things actually hold to what we have shown before, because our techniques just simply fail there. Another open question is of strong error reduction. So we know for QMA that you can have strong error reduction. So you don't need to increase the proof size to actually increase the promise gap. And we can actually show in this work, when actually you have near perfect completeness, you can use a gentle measurement lemma to get actually some form of strong error reduction. But it's still an open question whether actually general quantum PCPs are able to have strong error reduction, or whether you can show some no-go result that this is not possible. That's all I had to say. Thank you.
Any question?
So this Muslim lemma that you mentioned, is it deterministic then?
Yes, yes, deterministic. Take a solve, yeah.
Better.
Yeah.
Thank you for the talk. I was wondering, when you talk about learning the Hamiltonian, how do you get access to the Hamiltonian? Like, what's your oracle access?
Yeah, so basically learning means that, so this QPCV verification circuit, that's basically something you have yourself, you have access to. Basically, this verification circuit, we show this induces a local Hamiltonian, but you have to learn it by running the circuit. So basically you run this verification circuit like many times, and that basically is basically the thing you access to learn Hamiltonian.
Okay, thank you.
Yes.
Any more questions?
I've got one more that's so basic that I'm afraid to ask. Could you explain again the PCP version of the local Hamiltonian problem? I didn't get how
Yeah,
it's
sure.
different from the standard one.
Oh, okay. I'm not going to go back, but the answer is going to be very short. With
That's why I was afraid it's a basic
no, it's totally
question.
fine. Yes, here. So it's different only in terms of the promise gap. So basically, this promise gap is this difference between B minus A. So you have to determine whether the energy is either large or small. And in the normal version for QMA, these energies have to be like inverse polynomially close together. Like sum inverse. So the point is there exists some inverse polynomial. I think originally it's, if the circuit construction is, I think 1 over, I think the number of gates you apply to the power 2 or 3, one of the two. So that's our polynomial in. And here it has to be constant relative to the operator norm. And it's also, I think it's also still open, like anything in between there is also still open, whether it's QMA hard or not.
Why does it make sense to think about this as like the PCP version of the problem?
Oh, it makes sense because if you have the classical PCP theorem, you can also think about, so if you have K set, you can think about, it also implies actually that, also the Nernst proof goes this way, that you can think about either like all clauses can be satisfied, or a constant fraction of them are not satisfied. Those are like the yes and the no cases. So that's why it's a quantum generalization of the classical PCP theorem.
Thank you.
Any more question? Okay, so let's thank speaker again.
Right, so desktop. And this is battery management, right? Power sleep settings. Power sleep settings, and then we say that when plugged in, this never goes
Never. Okay.
to sleep.
And sleep when plugged in. Never.
Plugged in, this never goes to sleep. That's it. And actually, yeah,
You can have
just
never.
in case
Or yeah.
when on battery, in case
Oh,
someone
yeah.
inadvertently
That's
plugged in.
true.
That's it.
Yeah, someone told me they are.
Hello, yes.
Hi everyone, welcome to the second afternoon session for today. Our first talk in this session is going to be by Joao Doriguello, and he's going to be talking about constant depth circuits for Boolean functions.
Cool, thank you for the presentation, introduction. Yeah, my name is Joao Doriguello. Today I'm going to be talking about constant depth circuits, mainly quantum memory. This is joint work with Jonathan Allcock, Jinge Bao, Alessandro Luongo, and Miklos Santha. So let's jump straight into the action. So what is a QRAM? So from a very theoretical perspective, a QRAM of size n is basically an oracle that does this mapping. So it has an address register I, a target register B, and a quantum memory register X, which can be, in this case, quantum, or it could be classical. And then If it's classical, it won't be writing in the cat notation. But what it does is that it accesses the xi entry, or the ith entry of the memory, which is xi, and adds to the target register. So you can see it as a quantum equivalent of a read-only memory. We also have another type of gate called quantum random access gate, which does semi-equivalent, but instead of reading only, it swaps a target register with a certain position of a memory in subposition. You can see this can be seen as equivalent of like a read and write gate. And QRAM and QRAG they allows us to access classical memory subposition. And why do you care about this? Is because they're very useful and used in many important algorithms. So for example, I guess everyone knows Grover search. You repeat your Grover's oracle many times. I don't know if you can there. I don't. There's no. I don't think there's a. There's a point. Okay. So okay, there's a. Okay, not in the best place. So you have your Grover oracle, and you do many times. But inside your Grover oracle, you have to do this phase oracle. And for normally to do this kind of oracle, if you rely on this on you're searching in an unstructured list size, you have to load your memory first, and then later you can do this phase oracle. You can also use in Shor's algorithm using window arithmetic for lookup addition. So for example, this lookup part, you rely on a QRAM. And many other applications, HHL type of algorithms. Quantum machine learning basically is like fundamental. And cryptography, collision finding, quantum random walks and graphs. So basically any algorithm that requires manipulating external classical data, unstructured data, in which you have to load the classical data into a quantum computer, you're going to rely on QRAM. There are many types of QRAM circuits. So for example, one I'm showing here is a multiplexer in which you try all the combinations sequentially, all the unitaries you need, until you load all your possible, your quantum data into your target. This one was class is very simple, but it's a linear depth, so it's not something we would like to. Another simple one is a fan-out architecture, in which is a tree-wise shaped circuit, in which each qubit of the address register is gonna control the path that your target qubit will take in all the layers. As I put it here. This is much better, has a low log depth, but it was shown that it has a low noise resilience. And there's a more sophisticated one, there's a bucket brigade, in which instead of having your address qubits control all your qubits from the target for a certain level of your tree, you can actually send down your address qubit down the tree to create a path, and such that your target qubit would interact with one address qubit per level. And has much higher noise resilience, as was shown by some papers recently. Okay, but the problem is that there's many difficulties with QRAM. So far, there's no experimental implementations, and I don't think there's any on the horizon. QRAM is costly, contrary to most RAM architectures. It might require error correction, which make it even heavier. And there's many critics pointed out by this, for example, this recent paper by Jackson and Ratio, in which they try to argue that if you require error correction, you're going to lose all your advantage, and is a point of a argument of lost opportunity in which you could probably trade your low quantum advantage with parallel class computations. So this is just to say that QRAM is very vital, it's very important for many algorithms, but it faces a lot of hurdles. And when you tell most people, especially quantum artists, say, I came up with a quantum algorithm, but realizing QRAM, everyone was gonna look down, and you're like, yeah, whatever, it's not gonna go anywhere. So we came with this, we arrived at this project, and we're looking at all these difficulties and saying how QRAM was important, and we decided to look at that. So I'm going to disappoint you if I say that we didn't solve this problem. We didn't come with any new model of QRAM that surpasses all obstacles. But we came from a more theoretical perspective, especially coming from like QAC0 constant depth circuits, and we decided to see what we could do with QRAM. So what we did in this project, we employ like special multi-qubit gates that I'm gonna talk about soon, to propose actually constant depth circuits for QRAM and more general circuits like these uniformly controlled gates, in which you apply a single qubit unitary to a target state, control on your address register, and Boolean functions. Okay. So what are these multi-qubit gates that we employed? These are very fundamental and have appeared before, like fan-out gate, which is basically a sequence of C-nots share a single control qubit. It's basically a copying. You can copy many single qubit into many other qubits as a cost of one C-naught. So that's fan-out will be a classical equivalent of just copying classical data, which is cheap classically, but not so much quantum. And the other one is called this global tunnel gate. It's basically a sequence of controlled Z gates with some phase. So instead of having many CZ gates separately, you can do these gates. You can combine all these committing gates into a single gate we call GT or global tunnel gate. So these are gates we're gonna be assuming that we can perform with like constant cost. And why they? First, because they tie very nicely to nice complexity classes that all people are going to be talking about in the next talks, which are QNC0F, QAC0F, and many previous works have explored the power of fan-out and GT gates in constructing basic Boolean functions like OR and threshold. There are physical proposals for this kind of gates in our traps, and there have been experiments carrying out implementing these gates in real life. So they're not out of this world. It's another question if they're going to be good in practice and when it comes to quantum computing, but they can be realizable. And to be honest, they're simple enough. I mean, they're the simplest qubits, multiple qubit gates I can think of. Just copying and CZ gates. Okay, so our tools that we're going to be using or we use in a paper is very simple tools. So first is that any single qubit gate can be decomposed as this sequence of phases sandwiched by Hadamard's. Another one is the equivalence between a fan-out and a parity gate. A parity gate being a gate that computes the parity of a certain subset of qubits and outputs the result into a target qubit. Other tools is these long constructions for the AND gate that was done by Hsieh and Taishu, Tani, and Sergey, and others. You basically can do AND gate in constant depth using basically linear n log n number of sealers and fan-out gates, or only 4 GT gates. And the final result that we use is that any pair of, if you have a bunch of pairwise commuting fan-out gates, you can basically compress or think them as just one GT gate. Okay, so what we built these uniformly controlled gates, which are basically these single qubit gates control on your target address qubit being a certain value. So they have this form, very simple, especially the matrix one. As a subcase of this kind of gates, we have the Boolean gates, which you think of your UX gate here being the Pauli gate, the Pauli X gate, and you end up with the Boolean function. So Boolean function is this what we call this F fan-in, so fan-in gate. You basically compute a Boolean value of your address, and you put in your target. And this includes many Boolean functions like n, or, majority, threshold, exactly, mod, parity. And finally, QRAM and QRAG, as I told you before. And we stress that QRAM actually is a it can be seen as a Boolean function. So QRAM is actually a subcase of F pending case and F pending gate. Yeah, which is this, basically this Boolean function of this form. So if you want to see in the picture how all these gates, these classes, they intercalate, I put it here. There's some classes here. These quantum memory devices and FQRAM, which we define in our paper, but I'm not going to talk about it. But as you can see, an FUCG is a very broad class that encompasses FNIN and also QRAM, but not all gates. For example, QRAG is not part of FUCG. Okay, so this is first construction. We propose two kinds of constructions for these gates. The first construction is very simple, is convert the input, your target input, into its one-hot encoding. So what is the one-hot encoding of a certain string? So take a string X, its one-hot encoding is like an exponentially larger string in which you're gonna place 1 at the entry entry in which its coordinate equals the original string X up to some ordering. And the rest of the string is all 0. So it's basically like a massive string with Hamming distance, Hamming weight 1. And using this construction, we propose that I will have this kind of resources. So for example, you can construct any FUCG by using these many fanouts and ancillas, or only 9 GT gates and these many ancillas. And same with FNIN, similar number of resources and slightly less GT gates, until QRAM can construct basically like a QRAM in like almost linear number of fanouts and ancilla, or only 6 GT gates. The results for FUCG and FNIN are worst case complexities. If you assume extra properties on your F, these results can be improved. So here I'm gonna like display the circuit that we have for QRAM. So it's very simple circuit. So this circuit does QRAM. So what you have as your address qubit, your memory qubit, and what you do, you start by what almost all the circuits on like QAC0 class does. Like you first copy your data many times. So you're gonna copy the address so that we can subsequently do stuff in parallel. So after the copying, we do the one-hot computation. One-hot computation can be done very simply by taking all the n combinations of your input and output and putting another target. So that's what we do. We do all the combinations. If your string is all zeros, we're gonna put a 1 here. If not, if they're like 1 and 0, 0, we're gonna put here until like you try the combinations. If they're all 1, you're gonna put here. So at the end of the day, in your auxiliary register here, you're gonna have at most 1 qubit being in the state 1 per branch of the wave function. And after that, what you have to do is just copy all these results into a target. So you could do this with many CNOTs, or more simply, just simply a parity gate, which this is a parity gate, like a base of fan out conjugated by Hadamard's. So you just put all your at most 1 entry into the target, and later you will compute, and basically voila, you have your B plus XY at the target. How many GT gates, for example? So you have 1 plus 2, so 3. Another one here, 4 plus 2, 6, 7. That's how we got 7. Very easy. And that was the first construction. The second construction is more elaborated, and I like the most. I think it's nicer. He explored this Boolean analysis connection between constant depth circuits and fanouts made by some authors almost like a decade ago. And we rely on 3 times of Fourier decompositions. So here we like have basically like 3 subcases, and that's why we have like this table with like many different quantities, like different expansions on a Boolean function. I'm gonna make it more precise in the next slide. But you can see like you realize each construction has its merits and pros and cons, and it's gonna depend highly on the function you're gonna decompose. And it's going to be very dependent on the Fourier spectrums and properties of your function. So that's why you have like the support and sum of the support. But okay, and the GT functions, they decrease a bit. Okay, but don't get caught into all these nasty expressions. The idea of decomposition is to expand your function in some nice bases. So for example, we can use the first very basic representation, which is the Fourier expansion of the reals. You expand a function in a parity basis, and you have this. Or you can approximate mainly your Fourier expansion that you have is not sparse. So maybe you can approximate to another function which has a sparse Fourier transform. Or you can think of let's not expand it over the parity basis, but actually let's expand on the end basis. So these are third representations. So why we care about this kind of expressions, these expansions, is because they expand a function or your original function into functions that we can calculate easily. So parity is easy. Parity is basically one C0. And n is basically, as you saw, it can be constructed by like a linear number of C0. So these things are easy to do. So the idea is that you reconstruct all your function on phases. So this relies on this very simple inequality that the product of a z or z gates or z with phases is basically the z of the sum of the phases. And this, if you're using the Fourier decomposition, turns out to be the original function. So you can reconstruct the original function on a phase of a gate if you control the phase that we know. You know this for each function you're doing. You just don't know the function of the parity for your input. So if you calculate these, you can control and reconstruct the phase. So more specific how you do this reconstruction. Suppose you calculate all the parities using fan out. Then you can create this cat state. And from this cat state, you can apply a control phase in parallel with all the other qubits onto different qubits. So basically, you apply like a control on each qubit onto the state, and you create this. And this is basically this. So you leveraging this cat state just to construct this in parallel. That's a trick, because you could have do it like in linear depth or log depth, but you can do this parallel using this cat state. The problem is that this cat state is hard to construct for a normal circuit, but for using fan outs or CT gates, this is easy. And then you compute the cat state, and voila. And you can do the same thing. You can see QRAM as a Boolean function, so you can do Fourier analysis. You can calculate all the Fourier coefficients and apply the same technique. And what you get that you can do with this construction, you can do QRAM with this many ancillars, slightly worse than using the first construction, like n square, basically, ancillar fan out. But using GT gates, you can perform that with only 2 GT gates. That's very efficient, in my opinion. With more ancillar. But the number of ancillar can be decreased if you use some recursion trick. Can be exponentially reduced at the cost of using more GT gates. Forgot the word GT gate here. Yeah, and I think I'll get into the end. I don't know if I rest or not. Oh, perfect. So in this talk, I show we propose 2 types of constructions for constant depth circuits for uniformly control gates, which as a subcase encompasses Boolean functions, and a subcase involve QRAM, not QRAG, but QRAG can be done using the first encoding. And this was done as a one-hot encoding and Fourier analysis with 3 expansions. And even though this doesn't truly unbounded gates won't be available or won't be a reality experimentally, maybe you cannot do fan out on like 10 billion gates, but maybe you can do like in 10 or 100. So this maybe can not make your circuits constant depth in practice, but can be shortened a lot just by replacing log 2 factors to larger bases. If k is the length or the size of your fan out. And that's it. I thank you for your attention.
Thanks for the nice talk. Any questions?
I thought everyone had understood the whole talk.
Hello. Thanks for the talk. Yeah, so my question is, at the beginning you talked about the different QRAM implementations and how some of them had this noise resilience. So like the bucket brigade versus the fan out. Since your circuit seemed to have a lot of fan out gates, is it accurate to say that it probably won't have these noise resilience properties?
Yep, probably, maybe not, probably not. I'm not too familiar with the analysis. I know the high noise resilience of the bucket brigade is that there's not much entanglement going on between the qubits in each branch of the wave function. So each address interacts with very few. The target interacts with very few qubits. So that's why. In our case, it's not clear. I'm not sure. You can try. You can. I'm inclined to say no. It won't be as good, even though you can say like maybe okay, it's constant depth. You won't have enough time to propagate all the errors if you click enough. But I'm not gonna put my hand on fire. So like no, it's noise resilience.
Okay, thank you.
Yes.
Any other questions? I'll ask a basic question maybe. So your construction using the, the really large encoding, whose name I forgot. Yes.
Encoding, yeah.
That needs 2 to the n ancilla. Isn't that bad?
Well, it depends. But it depends where you apply it to. The QRAM you're doing that for the address qubit, which is log n. So that's why I have n at the end. But yeah, in the worst case for FUCG, yeah, it's gonna be 2 to the n. But that's expected. Like this was even like for we didn't expect that to decrease the number of Scylla. I mean, what happens in these constant depth circuits in QRC 0, you're always going to increase the number of Scylla mostly. And even for like log depth circuit, the number of Scylla is in the worst case is like 2 to the n.
So, but then the other construction doesn't have this, right? Isn't it strictly better then?
No, the other constructions for in the worst case is 2 to the n, because the support of your Boolean function can be 2 to the n, could be the whole thing, right? It's slightly better. I mean, here's like n to the n, in the other is like 2 to the n. It's slightly better by a factor of n, Hsieh exponential in the worst case.
Thanks. If there are no other questions, we can thank the speaker again. Okay, hopefully there was enough time for people to come in from other sessions. Okay, we'll have our next talk now. It's going to be by Joel Rajakumar, and he's going to be telling us about polynomial time simulation of noisy IQP circuits.
Okay. Hi, everyone. I'm excited to be here. I'm going to be talking about polynomial time classical simulation of noisy IQP circuits with constant depth. This is joint work with James Watson and Yikai Liu over at the University of Maryland. So a lot of what motivates this work is quantum supremacy experiments. So you've probably heard of these before. They're usually tasks that are expected to be difficult for a classical computer to solve, and at the same time tractable for a near-term quantum computer. And some examples of these are random quantum circuits, which were implemented some time ago by the Google group, IQP circuits, more recently implemented by this Harvard Q-era UMD collaboration, and boson sampling, which is also implemented on hardware recently. And there's another hope with these experiments is that they're also efficiently verifiable as well. But I won't be talking too much about that part of it. What I'm going to be focusing on in this talk are the first two bullet points. Are these tasks difficult for a classical computer to solve? And are they tractable on a near-term quantum computer? So if you haven't guessed, I'm going to be focusing on IQP circuits. And what's an IQP circuit? Well, I start with every qubit in the plus state. So I have an equal superposition of every single computational basis state. And then I apply a diagonal unitary. This is diagonal in the computational basis. And this unitary is usually constructed with discrete gate sets. So for example, T controlled phase, Z, CZ, CCZ. These are examples of discrete gate sets that can generate such a diagonal unitary. And you'll find a lot of these in literature. And finally, you measure in the Hadamard basis. So you do your state prep and your measurement in this Hadamard basis, and then you do all of the intermediate gates diagonally. So what was found like back in 2010 is that these circuits are hard to exactly sample from after a depth of 4. And this makes them a good candidate for quantum supremacy experiments. This was improved later on to show that it's hard to approximately sample from these in the average case under some conditions. And all of these like hardness statements usually rely on some complexity theoretic assumptions like the polynomial hierarchy. But this is what's known sort of about this hardness. And then another thing that makes it more practical is that it doesn't require a universal gate set. So this hopefully makes it more amenable to near-term hardware. And this is sort of the intuition for the recent Harvard Q-era UMD experiment. This fact is sort of what goes into that a little bit. Now, when you implement these circuits, you have noise. And the way we're going to model noise here is every single gate is interspersed with independent single qubit noise channels after. And I'll define these noise channels later on. But you have your circuit and you just have noise acting throughout your entire circuit. You don't do, in this model, we're going to say you're not supplying fresh qubits and you're not doing intermediate measurement with feed forward. And that's sort of important. What we're considering here is just you run a circuit and you're not correcting your noise, but you're hoping that this noisy circuit still does something non-trivial, something that demonstrates quantum supremacy. So what's been shown already is that for a particular class of IQP circuits that with an anti-concentrated output distribution, these circuits become easy to classically sample from when there's noise. And these results were extended later on to noisy random quantum circuits. And again, you have to assume this anti-concentration property. So what sort of, the main question that I'm going to try to answer here is, under what conditions can we classically simulate IQP circuits with uncorrected noise? And then that result sort of shows that the anti-concentrated circuits are not robust to noise and admit classical simulation. And so the question is like broadly, what sort of IQP circuits can you simulate when you have this uncorrected noise? The motivation for this is twofold. The first thing, the most sort of obvious thing is that it lets you assess near-term quantum experiments. So it tells you, are these circuits actually infeasible to classically simulate? Somebody with the hardware tells you that they just did a supremacy experiment. You can try to spoof it and see whether that's actually true. The thing that I think is more interesting, though, is that it actually would also help guide future experiments. If you can develop good classical simulation algorithms with polynomial time runtime, that sort of take advantage of different aspects of the circuit you're running. This sort of tells you what aspects of the practical implementation make it easy or hard. And hopefully this guides how you actually implement it. So sort of what we'll see in this talk is that the IQP-ness of this circuit gives it some non-robustness to noise. So the main result here is a polynomial time classical simulation algorithm for sampling from the output distribution of any IQP circuit beyond an O of 1 depth when single qubit polynoise of constant strength is interspersed between gates. So to place this in the context of existing results, imagine having circuit depth on this axis. And what's been shown before, like 20 years ago actually, is that if you go past a depth of log n, your distribution with this uncorrected noise model becomes close to uniform. So you're already trivially classically simulatable. And surprisingly, there's not a lot of results that go to very far below this depth threshold. So in the case of IQP circuits, we know that with anti-concentration, in the average case over these anti-concentrated circuits, if there's noise, you're classically simulatable. What our result shows is that at a constant depth and beyond that constant depth, you get classical simulatability. So I'm gonna stress the generality of this result a bit. So it applies to arbitrary circuits, including all-to-all connectivity. It applies, so I didn't define the polynoise channel explicitly because it applies to a broad set of channels that include a dephasing component. And what this means is if I can express my noise channel in a way that I can extract out a dephasing component, then it fits into this classical simulation algorithm. Depolarizing noise, for example, is something that you can write as dephasing and bit flip noise. So you could simulate a circuit with depolarizing noise. That's the math equation for that. And it also applies for any IQP circuits, like any diagonal gate set you use to construct your IQP circuit, as long as each gate acts locally. So again, I'll stress it doesn't require anti-concentration. And since I didn't define it before, this is a little hand wavy, but it just tells you, anti-concentration sort of tells you over an ensemble of random circuits, how flat is your distribution. And this is sort of the formal definition of it. It comes up in proofs of hardness and easiness, but it's something we're not going to need for our classical simulation algorithm. So I won't go too much into it. So to show you how it works, I'm gonna go through an example case. So suppose you have an IQP circuit constructed with T gates and controlled phase gates, and you've interspersed dephasing noise. The algorithm is gonna work in 3 steps. These are just the titles, and I'm gonna explain each step. So the first fact we're gonna use is that dephasing noise commutes with diagonal gates. So if you have your circuit and you have interspersed dephasing noise throughout your circuit, you can take every single dephasing noise channel, commute it to the beginning of the circuit. And now you have this larger strength dephasing noise channel at the beginning because your noise builds up. And this is sort of taking advantage of the commuting structure of the IQP circuit. The second fact we're going to use is that dephasing noise acts very predictably on this superposition state. So the plus state is a superposition of your 0 and 1. When you put dephasing noise on it, it makes it a mixture of your 0 and 1. So in the block sphere picture, what used to be on the boundary of your block sphere is now a shorter block vector, which is a mixture between your 0, your 1, and the plus state. So the idea here is instead of simulating the shorter block vector, we're going to sample. So your simulation algorithm is going to take your noise channel and sample from it as either leaving the plus state intact or an error occurs. And this error replaces it with the 0 or a 1. So that's how we're going to simulate all of the noise that we built up on the beginning of the circuit. The third fact we're going to use is that diagonal gates act classically on computational basis states. So T gates introduce global phase that can be ignored. The controlled phase gates become classically controlled phase gates, which don't introduce entanglement. So once you've sampled your 0s and 1s, these errored locations, the controlled phase gate that acts on these errored qubits acts classically. You have a controlled phase, a classically controlled phase. So this has all been known before to some extent, that noise acts in a way that basically replaces some of your input states with random zeros and ones. But it takes a while, like a large depth, for you to get to the place where most of your qubits are zeros and ones. And this is what I was talking about earlier with the log n depth. And it takes log n depth for most of your qubits to become 0 or 1. The trick here is we're not going to wait for most of your qubits to become 0 and 1. We're going to cause percolation in the connectivity of our circuit. So what this means is I'm going to define an interaction graph for my circuit. Every qubit is a vertex, and there's an edge between two vertices if there's an entangling gate between qubit I and qubit j. I'm stressing entangling because of this fact that I mentioned earlier that like some of these gates become classical controlled gates, which don't introduce entanglement. So each dephasing error removes all the edges of the corresponding vertex from the interaction graph. So if this was your earlier interaction graph, every time you have a dephasing error and you replace some of your qubits with zeros and ones, those edges get removed from the graph. Your controlled phase gate becomes a classically controlled phase gate, and you can classically simulate this. There's no entanglement between the different regions. The other thing you can notice here is that what used to be this giant connected component with entanglement stretching across the entire circuit is now split into smaller components. Because there's no entanglement across these two components, you can simulate them independently. And that's the trick. Essentially, we're going to check the depth at which all of our circuit gets percolated into many small independent sub-circuits that we can simulate independently. So when does this happen? So from graph percolation theory, we know that for any graph, if delta is the maximum degree, and Q is a probability that the vertex survives, so that you're not removing its edges, when Q times delta is less than 1, percolation happens. So your connected components become smaller than log n with high probability. So in our setting, in this graph that I just showed in the previous slide, your degree of your graph is bounded by your depth. And the probability that your vertex survives, that a qubit remains non-dephased, decays exponentially. And this is sort of important. It's because like there's a certain probability it survives the first layer. Yeah, I'll just use this, yeah. Wait, it's, okay. All right. Yeah. Okay, so, yeah, so there's a probability. There's a certain probability it survives the first layer, then it survives the first and the second layer, and the probability it survives D layers is exponentially decaying in D. So the phase transition occurs when e power minus PD times D is less than 1. So you have an exponential decay caused by the noise and this linear growth in entanglement, which characterizes the entanglement. And when this is less than 1, you see percolation. This will happen at a constant depth. So after a constant depth, all of your subcircuits are of size O of log n, and you have a polynomial time classical simulation algorithm. And I want to emphasize this point here because it's sort of getting at the heart of what this classical simulation algorithm takes advantage of, is that your entanglement in this IQP circuit is sort of growing linearly in a sense. It's growing with depth, but the noise is growing exponentially. So in this fight between noise and entanglement that we're trying to characterize here, noise wins at every layer. You're not introducing more correlations than the noise is taking away. So after a constant depth, you split into smaller subcomponents and you're simulatable in polynomial time. And this is whatever you do in the IQP circuit, this works for. So to summarize the algorithm, you sample locations of dephasing errors, you randomly replace the errored qubits with 0 or 1, replace every CS gate with a classically controlled gate, C phase gate, and simulate the resulting subcircuits independently. So now you might wonder, is this result tight? Can you do better than this? And in order to show that this is a tight algorithm, you have to show that there's hardness below this depth threshold. So I've said that above this depth, they're classically simulatable. And the next question is, below this depth, is it hard to classically sample? So is it hard to approximately sample from a noisy IQP circuit at a depth below this threshold? And this is actually a very big problem, because if you could do this, you would actually show a NISQ circuit that provides scalable quantum advantage for sampling. So this is a big open problem. And that would be what was necessary to show tightness. Instead, we can show something close. We can show hardness of exact sampling. And this is usually easier, much easier to prove. So we show that you can find hard circuits that are hard to exactly sample from at this depth. And this depth is theta p minus 1 log p minus 1. That's the exact depth threshold that for our classical simulation algorithm. So this sort of shows that it's somewhat tight. You might be wondering, well, does your classical simulation algorithm do exact sampling? And it does. And this is because we can formulate our classical simulation algorithm in two ways. It's an exact sampler with a random runtime, which is polynomial in expectation. This is called a Las Vegas algorithm. And you could also alternatively formulate it as an approximate sampler with the polynomial runtime. This second one is what you've probably seen in literature before for simulating noisy quantum circuits. But the Las Vegas algorithm implies the Monte Carlo algorithm. So the Las Vegas algorithm is sort of a stronger statement. So we're able to show this exact sampler, and we also are able to show hardness of exact sampling below that threshold. So for exact sampling, we sort of have a asymptotically tight result. The open question is it tight for approximate sampling? One important implication of our result is that it provides limitations on near-term fault tolerance models. So if you consider, this is sort of what you might try to implement in the near term, is you have a noisy physical circuit that encodes a logical quantum circuit, where the logical output distribution can be recovered through just classical post-processing. So you don't do any measurement and feed forward, and you don't supply fresh qubits, and this sort of fits into the definition of NISQ. And what our results show is that such fault tolerance can't be scalably achieved within the IQP framework. If it could, then you could classically simulate it with our algorithm. Now, to get to the numerics of this, how does this algorithm work in practice? The good news is the expected runtime doesn't depend on the noise strength. So there's no like exponential and inverse noise strength that you might see in other algorithms. The bad news is this critical depth threshold is actually very high. So this is a plot, for example, where for this case that we took, where we have T gates and controlled phase gates and you have dephasing noise, if you have noise of strength 0.01, so that's 1% dephasing noise, you get classical simulation at a depth of about 300. And for an experimentalist, this might seem kind of trivial. It's like, yeah, I sort of expected that after order 100 layers with 1% noise strength, it would be trivial. But this result kind of shows that this is true regardless of the number of qubits you have. And that's what's important about it, is whether you have 1,000 qubits, 1,000,000 qubits, billion qubits, you cannot encode enough redundancy to escape this 300 depth threshold that you get at a noise strength of 1%. If you run numerics on this is what a phase transition looks like. It's going to be, I couldn't explain this to you in this much time, but to conclude, we show that noisy IQP circuits are classically simulatable when their depth exceeds a constant threshold. The important takeaway from this is that if a fault tolerance protocol for IQP circuits should leave the IQP framework in some way, some of the ways you could leave it are doing intermediate measurement with feed forward, supplying fresh qubits, or implementing non-diagonal gates in between. Some future directions that I think are interesting is to think about what other families of noisy shallow circuits are simulatable. So the interesting thing here is we've taken a non-universal class of circuits, IQP circuits, and shown that it's not robust to noise. Maybe other non-universal classes also show the same amenability to classical simulation. So again, it doesn't need anti-concentration, and recent work has actually applied this to linear optical circuits, and a similar thing happens. So that's my talk. Thank you.
Thanks for the nice talk. Questions?
Well, thanks for the talk. Something I didn't quite get is like when you replace a qubit with like 0, 1 state, are you like exactly simulating the noise on that, like you're approximating? I didn't quite I didn't quite get that why you're doing that.
Yeah, so it is an exact simulation. Basically, the noise model that when you have a dephasing noise model, with a certain probability, it replaces you with plus. It takes your plus state and replaces it with the 0 or a 1. So what we do is we flip a coin with that probability, and if you have an error, then you replace it with the 0 or a 1. So that's an exact simulation as long as you know that error probability.
Other questions?
Following to that question, if it's exact, then how it can remove the entanglement? If the dephasing error, if I understand correctly, it introduces entanglement, and when you replace it with 0 and 1, and somehow it removes the entanglement, maybe my understanding is incorrect.
So you simulate the noise in this way by replacing certain qubits with 0s and 1s. If a qubit gets replaced with a 0 or a 1, those particular qubits now never get entangled with other qubits in the rest of the circuit. So once you've replaced in this diagram here, this bottom qubit with the 0 or 1, every gate that acts on it after that doesn't introduce any entanglement. Okay.
So one question regarding IQP. So I think so in general, IQP is just that our gates commute, but now you were here fixed on just the Z, CZ, and CCZ gates. I guess it's universal, or is it? Would you get a different result if you have more general sets of commuting gates?
That's a good question. So this is like the one that's most commonly I've seen in literature. You could also do it in the X basis. And then what you'd find is just the noise model you'd have to consider is different noise models. It would still work for depolarizing noise, but here we look at dephasing noise, for example. And if you took in the X basis, it would be bit flip errors that make you susceptible to classical simulation. So the result still holds. It just holds for a different noise model.
And do we require that like the whole gate set is commuting, or could we, let's say, have non-commuting gates, but then they are on different registers so that these gates specifically commute at the places they are, but otherwise not?
That's a good question. I'm not sure. I'd imagine if your depth was large enough on this section with commuting gates, then this result would hold. I'm not sure what happens when you on the registers with the non-commuting gates.
Thanks.
Hi, thanks for the really nice talk. Just like a fairly naive question, but you talked about this like sense in which the noise kind of wins against entanglement at sort of every layer. So if you kind of went beyond constant depth, would you expect any of these sort of like fragments of the circuit where you have some connectivity to remain of like non-trivial size, or would eventually it all go to like some completely decoupled kind of picture?
So I think if you keep increasing the depth, eventually, so this log n, if you go to log n depth, everything becomes random essentially. Okay. So your components become of size 1.
Okay, thanks. Yeah, cool.
If there are no further questions, I guess we can thank Joel again. Thanks for the nice talk. Who is the next speaker? Are you the next speaker? Oh.
Should I try?
Okay, the next talk is going to be by Michael de Oliveira, and he's going to be telling us about quantum circuits surpassing bias threshold circuits in constant depth.
Thank you for our presentation. So I'm Hsieh. I'm presenting this work about shallow depth quantum circuits. This was joint work Min-Hsiu Hsieh, Leandro and Subramanian. And now starting with our more general motivation that we have in quantum, which is showing and identifying computational problems for which quantum computers have advantage over classical computers. And normally we are most interested in those which are of exponential magnitude. And so in computational complexity terms, we could identify problems that are in BQP and not in BPP and P. And P and BPP are efficient classical computations, so computations that run in polynomial time, deterministically or probabilistically. And BQP are the ones that we solve efficiently on quantum devices. And here we know, for example, Shor's algorithm that can do that. However, it requires large fault-tolerant quantum devices. And this issue has been addressed by finding problems as the ones that have been discussed in the previous talk, and one of them being boson sampling. And it has shallow depth quantum circuits, and it's also separating these classes. However, both of them require some assumptions. So we cannot really prove them without assuming something, some computational statement that normally are well-founded, but we need them. And now we can motivate the question of removing the reliance on the assumptions, weakening the assumptions, or trying to see which kind of statements you can do unconditionally. So for what can we prove that quantum is better than classically without relying on any assumption? And as in the classical case, this exists for shallow depth circuits. So let me introduce you NC0. NC0 is the class of constant depth classical circuits with classical gates of bounded Van-In, and those are normal gates like and or and not. And then we have the quantum equivalent, where we have constant depth quantum circuits with single and 2 qubit gates. And here we had some years ago a breakthrough result by Ravi, Gosset, and Koenig that showed that exists a problem that can be solved by QNC0 circuits, so constant depth quantum circuits, that cannot be solved by NC0 circuits, so the classical equivalent. And it's very interesting because first of all, it's near term, it's shallow depth, and it relies on no assumption, no computational assumption. And furthermore, it was even shown to be noise robust, meaning that we can assume local stochastic noise, and this advantage still survives. With a different problem, but it still is possible to separate these two classes. And now the main critique that we could do here is that NC0 is rather a weak computational class. Now in circuit complexity, the next class that we would like to look at very naturally is AC0. So here we have, again, a constant depth classical circuits with AND and OR gates, but the AND and OR gates have unbounded Van-In. So we can feed as many inputs to a gate as we want, but it has to behave as an AND and an OR. And here was a very significant result too. So Adam Menwat and his collaborators showed that we can solve a problem with QNC0, again, constant depth quantum circuits, that AC0 circuits fail to solve, even in the average case hardness setting. And this recently was also shown to be noise robust. There will be even a talk tomorrow if you're interested to attend this. And now the main critique we could do again is that AC0 is rather of small practical use. We don't know a lot of computational processes that we can solve there. And now the next interesting class that we could look at is TC0, so constant depth threshold circuits, where we have as a minimal element a threshold gate. So this is a gate where we have the activation of the gate to 1 at a certain Hamming weight, and then we have a circuit of unbounded Van-In gates of this type. And why is this interesting? Because TC0 already can solve some interesting algebraic problems, like integer multiplication and sorting. And it was actually motivated to define and describe neural networks as circuits. And some recent results have even been shown that large LLMs and even ChatGPT, this type of models, are captured by circuit classes like TC0. But here we have the main issue is that we don't have strong lower bound techniques to prove that certain problems are not in this class. And since its creation or its definition in the 80s, we only have quadratic lower bounds for depth 2 and depth 3, and for arbitrary depth of superlinear wiring. And to insist on the hardness of finding lower bounds for the circuit classes, we had some breakthrough result in 2016 by Ryan Williams that showed that ACC, so classical constant depth circuits with and arbitrary mod gates, which is not more powerful than TC0, cannot solve problems in exponential time theory machines with NP oracles. So it seems kind of a trivial statement, but even proving this was a breakthrough. And now what we do is that we alternatively explore a class that was recently introduced by Kumar, which we call bounded polynomial threshold function circuits that has a certain parameter k. And what's interesting is that this parameter k allows us to interpolate between AC0, so the class for which we know some lower bounds, and beyond TC0 even. So it has a non-trivial connection. Now defining it, this circuit class of constant depth is defined by gates of this type. So if you have a gate of the type OR, for any input which has a Hamming weight smaller than k, then we can map it whatever we want, so with any polynomial of degree k. And if the input string has a Hamming weight larger than k, then we have a trivial behavior of OR gate, and it has to be a 1. So inversely, we have also AND gates of this type. And we can see that larger the k, the more computational power we have, because then we increase the region where we can do whatever we want, and we reduce the tail, which is trivial. And for instance, to see immediately that we get some non-trivial gates inside is that we get threshold gates that we can activate between 0 and k. And if k is super logarithmic size, it's already gates that AC0 circuits cannot compute. And now trying to show a little bit how this class relates to previous classes. So when k is 1, we get exactly AC0. When k is n, it kind of trivially computes everything because it can simply output any function that we want. But when k is of the order of just super logarithmic, then it's strictly larger circuit class than AC0, and it has a non-trivial overlap with TC0. And now, because this is a new circuit class, it would be nice to also understand how it relates more generally and what it can do. And in the first paper which introduced the circuit class, it was connected to linear threshold function circuits, which generally have been used in computer science to solve a lot of classification problems. And the relation is that with our parameter k, we can relate to which subset of these circuits we can compute, and it has a restriction on the weights. So the larger the value of k, the less restricted the weights are, and the more functions of this type we can implement. And what we did also additionally is that with a single depth 1 of this circuit class, we can approximate in this non-trivial region of the parameter k very general activation functions, for example, the k-ReLU. And now that we have defined our classes, we can actually already instantiate our results. And here we find a problem for which we can show that Q and C0 can solve. So constant depth quantum circuits can solve. And bounded polynomial threshold function circuits with a super logarithmic parameter k, so n to 1 over 5d, cannot solve. And this is a new and strictly larger circuit class than AC0. On top of that, we have even generalized this to infinite family of relation problems. Each one of them can be solved by a different qubit Q and C0 circuit in constant depth, while all of them fail to be solved with this classical circuit class. Now going a little bit through how we did this. So first we have to find the suitable problems to find the separation and prove the separation. And we can only rely on relation and sampling time problems because for decisions, Q and C0 and NC0 are even equivalent. So even the simplest classical circuit class is equivalent. So the first separation, for those who know a little bit about it, was related to this non-local game, the magic square. And the problem had the magic square problem built into it. And it was used to prove the separation. Then the separation with AC0 used a parity halving problem, where we are given an even input string, and we have to output a string which is modular 2 congruent with the Hamming weight of the input string divided by 2. And when the output string is of the same size as the input string, this is actually related to the generalized Mermin game. And what we did here is that we generalized the previous set of problems to arbitrary primes. And we call them the inverted strict relation problems, where we get an input string which is modular P congruent with 0. And the output string has to be modular P congruent with x minus x divided by P. And now we need to show that bounded polynomial threshold function circuits cannot solve these problems. So we start with our circuits. We apply a multi-output, multi-switching lemma to reduce them to decision trees whose leaves are sets of decision trees. And it's a set because each one of these decision trees computes one of the output bits. And then, okay, this is known to be equivalent to NC0 circuits. And for those, we can use old techniques, which is light cone arguments. And with light cone arguments, we can reduce this NC0 circuit to a non-local game over a subset of the inputs we started with. And for this non-local game, because it's this generalized Mermin game, for example, for the parity halving problem, we can then use classical correlation bounds that we have for the winning strategies, and we get correlation lower bounds for our circuit class. And our main contributions here is to define a multi-output switching lemma for this new circuit class, which allows us to reduce this object, and then defining the new non-local games, as well as the winning strategies, the optimal winning strategies, classically and quantumly. Exploring a little bit further the switching lemma. For those who don't know it, the idea of the switching lemma is that we fix some variables of the input, and then we look how the circuit was reduced. So we remove the gates that trivially evaluate already to 0, 1. And then we keep fixing variables, and we see at which rate the circuit simplifies to a trivial circuit. And what the switching lemma does, which is one of our contributions, is to show how we can fix variables such that we, with high probability, obtain this computational object, which is this decision tree with decision trees as leaves. And for this, we introduce a new multi-switching lemma, which is kind of the lemma which allows us to reduce a depth 1 of the circuit. And then this allows us to create a depth reduction lemma, which reduces the entire circuit for constant depth. On top of this, because we consider this family of relation problems, they will all be related to a specific family of non-local games. In particular, it's of the type of XOR non-local games. So we define them, and we define the correlation function with which any strategy relates to the winning strategy. And then we are able to show that any classical strategy that you can come up with has exponentially small correlation with the winning probability, with the winning strategy, while there exists a quantum strategy that maintains a constant positive correlation. So the last thing that is only missing is to create the quantum circuits that solve this. And here we take inspiration from the quantum strategy. However, the quantum strategy needs, the optimal one needs GHz states, and we cannot build them in QNC0. But we can build Buhrman's ket states. In this case, we need qubit Buhrman ket states, the generalization to qubits. We show that there exists a quantum circuit that can solve this, can create this states in constant depth. We apply the strategy, the measuring strategy with the inputs of the non-local game to this state. And then because we don't have a GHz state, but a local equivalent one, we get this additional inner products that completely randomize our outcome. But then we show that we can compute at least one of them and attach an additional correction to the outcome of the circuit, such that we can solve the relation problems. And so as conclusions, we have shown there exists a problem that QNC0 circuits, so constant depth quantum circuits, can solve, and that bounded polynomial threshold function circuits with a large parameter k, so super logarithmic, cannot solve. For this, we created a new multi-output switching lemma. Then we extended this to an infinite family of problems in higher dimensions, in all prime qubit dimensions. And for this, we created some generalization of the XOR non-local games, as well as proved the correlation bounds for classical and quantum strategies. Here we have a table comparing our result to previous ones. So what we have new is this new separation with this new class. We have this new family of problems, which creates new geometries with which we can solve the problems. We extend to higher dimensions. We get average case hardness also as in the AC0 separation. And in our preprint, we have even extended it to the noise resilient version, but it was not part of this talk. As open problems, obviously we could ask, we can make it noise resilient, and we have done this in the preprint, but we need all-to-all connectivity in the constant depth quantum circuits. So it's still open if we can do it with geometrically local circuits. We believed it should be possible, but we haven't achieved it yet. Then the obvious question is, can we extend it to a larger circuit class? Obviously TC0 would be interesting, but the classes of AC0P, so AC0 with a mod gate, seems to be a more tangible class to try. And then we have another question is, can we extend it to computational problems which are more useful? So this we're almost tailored to generate the separation, but there was an interesting result between QNC0 and NC0 for a decoding problem. So now we are questioning if we can do some interesting separation for something which will be practically useful. So some classical parallel computation that we can do it more efficiently on constant depth and parallel quantum devices. Thank you very much for your attention. If you want to have a look at your preprint, also please have a look at the concurrent work, which also generated our theorem 1 by Savi and Binyak. Savi is actually here. And they have also some other quantum separations. So it's also a very interesting read.
Thanks for the talk. Questions?
Oh, sorry.
Thanks for the nice talk. Just a quick question on the definition of noise resilience. In which sense you said your algorithm or proposal is noise resilient?
That's a good question. So considering the local stochastic noise model, you can make it, you can create the same QNC0, so the same constant depth quantum circuit, encoded in the surface code, and show that you can do run the surface code in constant depth. And then at the end, you don't decode the quantum circuit, but you can show that producing this output is still hard for the classical circuit class.
Thank you.
Thanks for the talk. A quick question. Have you thought about the class on AC0 Q of the mod gate?
With the mod gate?
Yeah, have you thought about it? I mean, you put it as a question, but have you thought about?
We have, and I think the
same techniques apply, or?
No, the techniques don't apply. That's why it's not here. And we don't have techniques for relational sampling problems. So for multi-outputs, we have some lower bound techniques for AC0P for decision problems.
Yeah.
Where the solution to the problem is 0, 1. So
Yeah,
you
yeah.
have simply to decide. But for multi-outputs, there's no technique. So
Your technique, where does your technique break?
switching lemmas don't apply to that circuit class. The mod gates,
Right,
if you apply some random restrictions, so we fix some variables, it doesn't guarantee that the mod gate will simply evaluate to 1 or 0. So for example, if you want to evaluate parity, you need almost to know the entire string to at the end tell if it's even or odd. So this type of techniques don't apply to AC0P.
I see. Fair enough. Any idea what to do?
I think so. Like for the decision version, there's this polynomial method. So you can interpret each gate as a polynomial. And then you can choose a field. And for example, if you have AC02, you can show that computing mod 3, for example, is a high degree polynomial in F2. And AC02 can only create low degree polynomials. Then this is the way you can prove that mod 3 cannot be computed in this circuit
okay,
class.
yeah.
But generalizing this to multi-outputs and sampling is not trivial. It requires completely new ideas to do that.
Okay.
You can do polynomials for like multi-bit outputs if you just like, I don't know, maybe have a polynomial for each output bit or something, right?
Yes, but here, because the condition is that you XOR them at the end, this operation would increase the degree. And so you cannot notice if it's high or low degree. Everything is a high degree at the end. I don't know if I was clear with that, but this problem is very specific in hiding the difference between the degrees. And you cannot use that technique.
If there are no other questions, I guess we can thank the speaker again. Okay, we'll start the last talk of the session now. Our last speaker is Joseph Sloat, and he'll be telling us about parity versus AC0 with quantum preprocessing.
Thanks so much, and yeah, thanks for sticking around. Last talk of the day. Hope you've enjoyed everything so far. So this talk title is like fairly technical. We have all these very concrete, specific things, but really, I hope that this talk can be more about understanding the relationship between structure in computational problems and quantum advantage. So when does structure allow for quantum advantage, and when do we retain quantum advantage with no structure? So if we think back to some of the very early examples of quantum computing being realized and being understood to be very powerful in comparison to classical computers, this was originally in the query models. So things like Bernstein-Vazirani problem and Simon's problem show these really kind of wild speedups with a quantum computer. And if you, and then, you know, there have been many, many more of this kind. So these are some decision problems about an oracle or some black box function. And if you look at them, you start to notice that structure of the promise is really important. So in Bernstein-Vazirani, we're promised that the function is secretly linear. In Simon's problem, we're promised that it's either one-to-one or periodic. And so you may start to wonder, okay, maybe these promises, these restrictions on the type of function that's hiding in this black box actually are fundamental to having quantum advantage. And that relationship has been also explored a fair amount. And surprisingly, well, maybe not so surprisingly these days, but a fundamental result in this area is that actually, if you consider unstructured problems, so here these are query problems, but where the function is let's say, drawn from a set of functions that's at least a constant fraction of all functions, that there's only at most a polynomial quantum advantage. So there is some quantum speedup, but it seems like for decision problems, you can't do much better with a quantum computer. On the other hand, much more recently, in the world of search problems, the breakthrough result of Yamakawa's entry showed that for search problems, you do retain an exponential quantum advantage. So somehow the relationship between structure and this quantum speedup, seems to be this pattern of where if you remove structure from your problem, there becomes a dichotomy in quantum advantage. You still have quantum advantage for search problems, but not for decision problems. And the next question you could ask is, well, is this just some strange artifact of oracle models? You know, we like this model because we can prove things, we can really settle some theorems, but maybe, you know, maybe it's just unnatural, and this is an example of it behaving unnaturally. And if you continue to search for settings where we can actually prove things without assumptions or conditions, you might look in the world of shallow circuits. So certainly in classical complexity theory, we can prove things definitively here that we can't prove for general computation. And we can keep filling in this table. So this, as we already heard in the previous talk, there's been this lovely sequence of works that is continued in this very conference of showing that constant depth quantum circuits are much, much stronger than constant depth classical circuits for an increasingly powerful classes of classical circuits. But, you know, there's a final box here. And if we believe this search versus decision dichotomy is actually a true feature of quantum computation for unstructured problems, we should expect that there's no advantage here. So one might be led to conjecture that is, you know, at most polynomial quantum speedup here. And this work is a first attempt at trying to prove something like this. I'll also say from a techniques perspective, this final rectangle here is the only rectangle where we need to prove a quantum lower bound. So I hope this complexity theoretic motivation is interesting from a more technical standpoint. I think also this is a good concrete setting to start thinking about circuit lower bounds against quantum circuits. So let's formalize this conjecture a little bit more, because if we think about QNC0, constant depth quantum circuits solving decision problems, there's a little bit of an issue. And that issue is if we think about constant depth quantum circuit, it's making a decision. So we need to read one qubit to conclude something. Well, any constant depth circuit, a single output qubit is only a function of constantly many inputs. So alone, it's kind of a nonsensical question to ask, could there be quantum advantage for decision problems with QNC0, because they can't really do much on their own. However, we can enhance this model slightly to make the comparison interesting. So in this work, I consider the following upgrade to QNC0. So we still have the QNC0 circuit, but then instead of measuring a single qubit to make a decision, we measure all of the qubits, and then we post-process with some classical computation. So this model is AC0 composed with QNC0, and we will like to compare it to AC0 alone. So I contend this comparison is a natural one. For example, AC0 composed with QNC0 contains AC0. So we can just ask about how much larger are the classes of decision problems for the left class. And also it's concrete enough that some things should be within reach technically. And another way to think about this question is, well, we know QNC0 beats out AC0 for search problems. Can this post-processing by this classical function take advantage of this search prowess and collapse that power down to a single decision bit to beat out AC0 alone? Okay, so now that we have our model settled, let me sketch how one might now formalize the conjecture itself, but there's no advantage. So F here is the classical post-processing function. Let's see if I can. F is the classical post-processing function. C is the QNC0 circuit. And measuring C, as we're doing in this model, leads to probability distribution. So F composed with C is a random Boolean function. And I'd like to just talk about the expected value of the output as living between -1 and 1. So when you think of this thing, this expectation of F composed with C as a map from the hypercube to the interval -1, 1, now you can express it using Fourier analysis and talk about its Fourier tail. So I'm going to talk about the Fourier tail for like one slide. It's not super important for the rest of the talk, but for Boolean functions, understanding the the magnitude of Fourier coefficients for higher frequencies is like one standard way to characterize the complexity of the function. And so these Fourier tails sort of describe how much of the activity in this Boolean function is high frequency. And it's a gem of classical computer science, which states that for AC0 functions, it's like nothing's going on in the Fourier tail. So the total Fourier mass in high frequencies decays exponentially as you look farther and farther down the tail. And with this very nice characterization of the power of AC0, with this intuition that this quantum model has little advantage, we might expect the same thing for our class AC0 composed with QNC0. So this I contend is the natural way to formulate a no advantage conjecture in this concrete complexity world. But this so far for general QNC0 and AC0 is it has really resisted proof. So we're going to work with what has to be a necessary corollary to any conjecture of this kind, which is that this composite model, QNC0 and AC0, cannot compute parity very well at all. So this is usually expressed in correlation. So I sample a random input. What is over my choices of Boolean function F implemented by AC0 and choice of quantum circuit C, that's constant depth. What's the highest chance that I'm correct? So the conjecture is that my advantage over just a random guess over the choices of inputs of computing parity decays to just 0. So I'm essentially no better than random guessing. And in this work, we prove the following. And so we were able to handle several special cases. So when QNC0 has no ancilla, so the QNC0 circuit itself is a full unitary from the Hilbert space covering all inputs to the output that the AC0 circuit sees. When QNC0 is ancilla free and AC0 is allowed to be arbitrary, we do in fact get this correlation. So this correlation decay. So not only is it little o of 1, but it absolutely races down to 0. And this is this looks quite a bit like what it would be for AC0 alone. So we find that if QNC0 has no ancilla, there is no advantage, at least for this parity computation. On the other hand, we can handle QNC0 being arbitrary, including with ancilla, at the expense of making some assumptions about AC0. So here, we've assumed that there's only linearly many gates in our AC0 circuit. Of course, AC0 has unbounded fan-in, so this is still fairly interesting. And we get a negligible correlation, so smaller than any inverse polynomial. Now, this second case actually is kind of a corollary of a slightly more technical case. So again, any QNC0 circuit, but instead of bounding the number of gates in AC0, we can instead bound this measurement of complexity of the function implemented by AC0. So if you've seen approximate degree before, it appears in a lot of communication complexity or query complexity for quantum circuits, but it's usually about the function that's being tested or queried by the quantum computer rather than an AC0 circuit. So this is maybe the first time approximate degree has appeared in quantum circuit complexity. And here again, we get a decay down to 0. And last thing I'll mention is that these bottom two cases, it's a little bit stronger than this. Actually, they're true even when the QNC0 circuit gets arbitrary quantum advice. So there could be a state that takes exponential circuit complexity to produce. As long as that state doesn't depend on the input, so it's really advice, it doesn't help at all. From a techniques perspective, this first row is by Fourier analysis, and the second two are by reductions to ideas from non-local games, and eventually a notion of k-wise indistinguishability, which first appeared in cryptography. I'll just also mention that this question about what is the approximate degree of F? Is it little o of n? This actually could be all of AC0. So modulo settling this approximation theory question about AC0 circuits, this might be settling the whole parity conjecture. And this is a large open problem. Several researchers have spent 10 years on this question, and it seems very difficult. Okay, so the proof of this first row, when we assume that QNC0 has no ancilla, is actually there's kind of a brief visual proof of it. So I'll present this now. So I'm going to use this pictorial notation on the left-hand side here. Remember, this is a randomized function because it's not pictured, but we have our circuit, and then we're measuring all the qubits and post-processing with the function. But so implicit here is that I'm actually talking about the expected value of the output of this computational model. And this is an inner product, which just means take the expectation with respect to input here. So, but we'll keep working with this picture. So the first step in the proof is to note that when C is itself a unitary, we can take the adjoint and take C, flip it around, and precompose it with the parity function. So these two inner products are equal to each other. And then I promised that there would be Fourier analysis, so we have to use Plancherel. So there it is, just put the hats. And again, this is the same inner product. Now we can start thinking about how to estimate this quantity. So we know F is an AC0 circuit. And again, this gem of classical computer science says that the Fourier spectrum of any such function decays really aggressively as we move higher up in the size of the Fourier coefficient. And now we can think about, well, what about this other composition of functions? And so we want to fill in this picture. Now, parity alone, if we just look at parity, that is one of the Fourier basis functions. So it's the Fourier spectrum is a point mass on the farthest right entry. And there's a quick lemma you can prove that says if I precompose parity with a constant depth circuit, that Fourier mass can't bleed down very far. It only bleeds down to a level that's a constant fraction of n. So now we have an inner product between two vectors with almost disjoint support here, and we can thereby bound the inner product with a very small number. Okay, so that's the ancilla-free case, but it does not extend beyond because it really relied on being able to take this adjoint and know it's the same inner product. So what do we do in general? So I have about 3 minutes. I'm not going to be able, unfortunately, to talk about everything in detail. But the point is that you can take your original circuit model here with this QNC0, and through some light cone and graph theory kind of argument, actually reduce it to a different model here that looks more like a non-local gain. So here I still have an AC0 circuit, but the input is no longer QNC0. It's the output of a bunch of players. So each player gets a single bit of that input. They each output a constant number of bits. And they share here, as I've written, they share no signaling correlation. So this is a little bit stronger than quantum correlations. The version with quantum correlations, that being hard would also imply the theorem, but it suffices for this work to allow strategies where all of these n players have no signaling correlations. And we want to argue that this model of computation here also cannot compute parity. And if you think about it and you think about how parity relates to the locality of this channel, which is this no signaling channel, you realize that any marginal of this channel that doesn't involve one of the players is going to be indistinguishable. So another way to say that is consider the push forward of the uniform distribution over even strings and the uniform distribution over odd strings through this no signaling channel. Then this correlation of this model with parity is just the difference of the expected value of f on these two push forwards as so. And like I mentioned earlier, the no signaling property of this channel n implies that if you look at any marginal of mu and nu that avoids at least one player, these two distributions are indistinguishable. And we know from Bogdanov et al., which is a paper in cryptography, that f is fooled by local indistinguishability of this kind, if and only if its approximate degree is small. So local indistinguishability is a lot like KY's independence, except instead of being indistinguishable from uniformly random, you're indistinguishable from some other distribution. And so this is how the approximate degree of AC0 comes in. So I will skip all of the specifics about approximate degree of AC0, but the main point is that It's a difficult question. There are upper bounds and lower bounds that look very tight. And I do include in the paper a slight weakened version of the question that might be easier to approach. And maybe I'll just conclude with one quick idea here. So there's the sense in which you can only choose two things in quantum computation. You only get to choose two of these three. So you can fill it in. This is what kind of another formulation of what we saw at the beginning. And then you can ask, well, what about the triangle for constant depth? So Adam Benet, Watts et al. And related work cover this edge. The present work is trying to fill in the middle. So that's kind of question one. And the other question you could ask is what goes here? I think these are all fairly interesting. So that's that. Thanks so much.
Thanks for the talk. We'll take questions now.
The weakening of the approximate degree question, does that suffice for what you're trying to show?
Yes.
And then, okay, I have a very naive question. In your pictorial proof where there were two steps, can you not what if you pad wires onto the parity gate? Like the adjoint breaks, right? Because there's a wire count mismatch when you have ancilla. Is that what you were saying?
Oh,
Why can't you just
why
pad?
does it break?
If I understood correctly, it's because the number of wires don't.
Yeah, it breaks. It breaks for like a slightly more abstract reason. So we could still allow end-to-end qubit channel that's not unitary. And the problem is you can always take an adjoint, but the measure with respect to which you have equality of the inner product, it's no longer like a uniform measure. And so in order to use the LMN result about the Fourier concentration, we need that we're actually talking about a Fourier transform with respect to the uniform measure. And so if you take an adjoint for something that's not unitary, like yes, you get an inner product, yes, you get these things formally, but it's no longer the second line here where I write adjoint, this is no longer inner product with respect to uniform distribution. So that's the technical piece. Okay, thanks.
Wait, but aren't the Fourier tail results for non-uniform distributions?
Yes, I think there are for certain ones, so like bias distributions.
Yep.
But I don't know, if you take the adjoint of a general channel, it's like the distribution could be so wild as to be outside.
You probably have to at least starting with some assumptions on the channel, right?
Right.
Exactly proper. Maybe if like one ancilla we should break.
Yeah, so probably for like constantly many ancilla, you can get something maybe even log, but I don't know how to go beyond log with this argument.
Hey, thanks for the nice talk. So the approximate degree of, it's me, I'm here. It's the approximate degree of AC0 that seems hard to give a lower bound on, but we do know the quantum query complexity of AC0 is omega n. So can you extend, so if you show that approximate degree being little of n would imply your conjecture, could you extend that result to saying maybe the block multilinear degree or like the completely bounded degree or the quantum query complexity is omega n, which we do know a lower bound of?
Okay, so wait, sorry, could you repeat the question?
Okay, we do know quantum query complexity of AC0 is omega n.
Yes.
But approximate degree is a lower bound on quantum query complexity, for which we don't know an omega n lower bound.
Agreed.
So can you reprove your, or like what's the barrier in proving your extending your result to saying quantum query complexity of AC0 being little of n implies your lower bound?
Oh, I see. I don't know what the barrier is specifically. I can tell you that so you'll see in the lower right-hand side here, there's this implication here that this implies the main conjecture. If you replace the right-hand side, it's no longer main conjecture. It's now actually for this model where I'm allowing no signaling correlations. Then this is an if and only if. It's an if and only if with the approximate degree. So in order to replace approximate degree with like quantum query complexity, I think one would need to understand more about what you're throwing away when you relax to no signaling channels, if that makes sense. So we don't need to go we don't need to actually bound the this version where there's no signaling channels. It suffices to bound the version where there are quantum strategies. But the quantum strategies don't reduce to approximate degree. Maybe the quantum strategies actually reduce to query complexity. I'm not sure. Yeah, it's an interesting question.
Thanks. Also, I have one more question. So you said your main result relates to your correlation with parity. So like, do we know anything about your main conjecture, for any bounded depth QNC0 circuits even?
Yeah, that's right. I think you can get for ancilla free, you can get like concentration on the last log n levels or something, but it's yeah, these are just kind of shaving things off of. It's like kind of direct extensions of these things rather than new ideas. Thanks.
Hello. In the case where like if you wanted to allow alternating layers of QNC0 and AC0, yeah, does it seem like you could maybe like for the just ancilla free case, could you, is there some sort of like induction argument or I assume I'm curious like how your thoughts on that.
Yeah, that's very interesting. I have no idea. And the reason, so the reason why some basic kind of induction wouldn't work is this thing Sabi asked about with the like what's the issue here with the adjoint is that if F here were replaced with okay, well there's a couple things. This like it depends on where you want to do things, but it seems like either you take the adjoint of all of the quantum things with classical functions in the middle, and then it's hard to make the argument that the Fourier spectrum of this composition stays at the top. Like if I had a layer of random, Boolean functions in the middle and other quantum things, it no longer looks like you can't make, because this is a light cone argument that allows me to bound how far this moves down. So that like falls apart. And then if you maybe don't swing everything over to the right, it's, yeah, maybe something can be done there, but
So like to clarify, it's because you kind of also ruin, like you also no longer have like your inputs are uniform once you apply one layer of AC0.
Yeah, exactly.
Cutter on Discord is asking why not all three vertices of the triangle can be satisfied. Both triangles, I guess.
Yes. So, okay, I guess it depends. So there's two triangles. The Fourier complexity triangle, not all three can be satisfied because Beals et al. Says that as soon as you enforce structureless questions, so there's no aggressive promise on the problem, then you can get at most, and your decision problem, you can get at most polynomial quantum speed up. And it's not arbitrary polynomial, it's like n to the 6th, maybe improved down to some smaller polynomial these days. For this triangle, it's all conjecture. It's up in the air, so yeah.
Any other questions? Okay, if not, we can thank Joseph again. And yeah, that's the end of the session. Thanks for sticking around till the end.